about Euclid and the simulations we're hoping to do for that satellite mission. But first of all, I thought I'd start off. Usually I get invited to these things to say things controversial, so I thought I'd start off by saying something reasonably controversial. Exascale n-body simulations, well, we all know what those are going to be, right? We're just going to do a large linear box, right? We always do, right? We just do the biggest thing that will run on the computer because it's boring and we know it'll work, okay? And that's because gravity is a long-range simple problem, so it attracts the computer centers because it's not like embarrassingly parallel, so they can claim it's a real need for these big computers, and that's what we're going to do. And that's why computer centers collude to run those things, because it's an easy way of filling their big new computer up with a proper calculation. And of course, we all know that those outputs are practically unusable because they're on the biggest machine you've got around, so they only just fit, so you generate far more data than you can ever possibly analyze. So only a small number of people can ever use them for anything useful. But, of course, they are incredibly useful for PR. That's one of the reasons why big computers get funded, right? Because then they can do these big problems. It's a circular thing, right? You need these big splashes, lots of publicity. We can run the biggest thing ever in the world, and that gets you good PR, right? Science content, usually minimal. Right, but that's what the exascale computing, that's what we're going to do. Anyway. Oh, no, I'm not going to say that. I'm not saying this. I agree, but I'm just telling you the practicality of what the exascale run is going to be. That's it. Anyway, roadmap to the full. Not everyone, just the first one. Yeah, exactly. It always is. Tell me the last 5 of those. They're always that. Anyway, roadmap to the full Euclid simulation. Yeah, something like that. So, Euclid's a European M-class mission. It's going to be launched 2020 odd. So the idea is to do some simulations to see what's going to happen, what I'd like to see with this mission. So you'll need something where you can do a mock sky, just like we saw earlier today. And so the idea is to simulate a portion of the universe that matches the Euclid mission. In order to do that, what you want to populate that with galaxies, so you need to be able to put galaxies in the simulation. And so the current idea is that you need to get down to about a particle mass of about 10 to the 9 solar masses per particle. In order to do that, that turns out to be pretty much the resolution of the Millennium simulation. And simulators and observers like that because they know all about the Millennium simulation. And if you say you're doing the same resolution as the Millennium simulation, they think, oh, well, that's believable. So we're going to go up a bit. So this plot shows you volume along the bottom against mass per particle up the side. And these lines are fixed n. Okay? So if you move down into this corner down here, the simulations get more difficult. You can, of course, always do these big, huge simulations, low resolution. You get very large n that way. Or you can do these very small, but expensive because they've got lots of because they've got very low spatial resolution, small spatial resolution simulations down here. So if you go this way, it becomes more difficult. So we're pushing a little bit with the full Euclid simulation into unknown territory, but not much. And we're talking about a few years' time. And the simulation we're talking about doing, if you just scale up that mass per particle to the volume you need, which is 4 gigaparsecs, you end up with 16,000 cube particles. So that's the simulation that we're proposing to do. So the numbers look a bit like this. 16,000 cubed, 4 gigaparsec. That's about 4 trillion particles. It's a little bit bigger than what's been done. Just to give you an idea of data volume, 128 terabytes per snapshot. Okay, so that's a lot of data for these runs. Processing hours to do that run, if you just take a guesstimate, it turns out about 500 million CPU hours per run. All that's sort of possible in a few years' time. Doesn't really push into exascale. That's the run that we're proposing. The tricky bit is this. I should stress I didn't write the Euclid blue book or whatever it is where this statement is made, but the aim of the Euclid simulations is to get to 1% accuracy between these k values. So between k equals 10 to the minus 3 and k equals 50, okay, in the power spectrum. So 1% accuracy is what we want. That's why we keep hearing 1% accuracy. And the problem is essentially everything in the whole pipeline has been, been looked at. The people have looked at their accuracy, and they've tended to get it roughly right to about 10%, pretty much everywhere. So getting down to 1% is tricky because you're pushing beyond where people have tuned all their work to date. But wait, I agree. I didn't write that, I should say. It's nothing to do with me. Anyway. What are the issues? Well, there's lots of places where you need to think about if you're going to get down to 1% accuracy. Your initial condition generation, we heard a bit this morning about initial condition generations codes. There are lots on the market. Someone needs to go and check that they do actually perform to 1%. Okay. Then you've got your production simulation, which I'll talk about in a minute. So you run different codes on the same ICs, and you see whether they recover the same redshift 0 power spectrum, etc. Then you've got post-processing. You have to look at where the structures are in the simulation, and then you've got to then put observables into the simulation. All of those things need to be done to this accuracy. So here's production. So our plan is to have 4 codes. Those are the 4 listed there. And we run them all on the same ICs, and we compare the power spectrum and the mass function. Okay. So is it believable? Can you get to 1%? Well, yes, you can. Top plot is the power spectrum, matter power spectrum, plotted against k. You can't read it. This is k equals 1, this is k equals 10, this is k equals 100. Okay. And what's plotted on the bottom is the residuals versus one of the codes. And there are actually 3 different codes in this. Okay. And as Joachim did earlier, this is a work in progress. We made this last week, I think. I've blanked out which is which, but it doesn't really matter. What you can see is that this is 1%. Okay, in the power spectrum. So up to k equals a few, 1 or 2, you can do 1%, pretty much. Beyond k equals 1 or 2, it's hard. Right, we know that. Okay, so to get to k equals 50 is a complete dream, even in the dark matter only. Okay, you might hope to get to k equals 10, dark matter only, if you're really, really careful. Okay, getting to k equals 50, total dream. Z equals 0? Z equals 0, yeah. Yes, this is different. They might all be wrong. Correct. All I'm saying is that you can get to 1% agreement between your codes. Yes, whether that's yeah. So 1% is tricky beyond k equals 1 is the message. Okay. What am I comparing? I'm just comparing one to the other. So this is the top one is the matter power spectrum for all the codes. Yes. 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 So that's why there are more than 3 lines. So we play with the parameters a little bit, play with the integration accuracy. This isn't, you have to play it a little bit even to get it this good. I'm just indicating that could you get to 1%? Yes, you could. You probably have to tweak your parameters a bit, and that costs you CPU. Because obviously you have to increase your force accuracy, play with the parameters. You need to run with these parameters if you're then going to stay at this 1% accuracy, is my point. But all I wanted to throw this up is that the softening somewhere over here, it's at k equals a couple of hundred, not a couple of hundred, k equals 50 odd for this box. Okay, so actually this break is at many, many softenings. Right, it's not at the softening. Yeah, well, it's of order of, it's a bit more than that. It's about 20 softenings, but it's not at 5 softenings or 3 or 4 or 4. Yeah. Yeah, exactly. It's the interparticle separation which is the key, not the softening. Interesting. We already mentioned this. Physics. Of course, this is dark matter only. What we want to do is physics. there's the problem is, what happens when you put baryons in, we've seen that already this morning, that baryons have an effect on the power spectrum at more than the 1% level. And we know the baryons exist. Right? Big shock. Baryons do exist. Neutrinos have a mass and they affect the power spectrum, and it kicks in around k equals 1. Above k equals 1, a bit of k equals 1. You better care if you're going to get 1% accuracy about the neutrinos. Marco talked about modified gravity, dark energy. We have lots and lots and lots and lots of people working on that. Right? We don't even know whether they exist. Right? Probably the signals cancel, right? But all these things affect you above k equals 1, so you better have some clue. So indeed, there should be some people working on all of these things. But my claim would be there should be more working on the baryons than on the modified gravity. Right? I'm not sure that's true. Here's the Baryon plot from Van Dalen. This is the, sorry, it's a different unit, but it's not my plot. Power spectrum along the top, K along the bottom. Here's the residuals plot. A AGN feedback model, A DM only model. So baryons basically. So the red and green curves are sort of different baryonic models. One with feedback and one with AGN and one without. What you can see is that beyond K equals 1, both of these have effect above the 1% level. So baryons can indeed have an effect on the power spectrum, and they can be significantly more. This is just an AGN model, but it's 10%. Okay, so baryons can have a significant effect. We need to understand them if we're going to get down to the accuracy of the survey. We're going to have a 1% survey. That's what they claim, right? They want simulations that are accurate to 1%. Okay. So that's production. Then we need to care a bit about post-processing. We need to reduce the data volume. Even these simulations, which are, you're skeptical whether you could call them exascale, you're still talking about 128 terabytes per snapshot. Okay, so you've got to reduce that. So Alex Knebber will talk a bit more about data processing later on in this meeting. We've also been working together on tree building, so that's how you link together the structures once you build them. That is indeed also not stable at the 1% level. Be very careful with how you link the structures together. And then we come to the really tricky bit, astrophysics. So then you've got to populate all these structures with observables, and you can do that in a variety of ways. So I've sort of ordered them in order of how much physics there is. So there's halo occupation, just throw galaxies in. There's sham modeling. There's semiotic models, which Richard has worked on. And then there's the gastrophysics, the sort of full Monte approach to doing the physics, throw in all the physics you know, and these become more and more expensive. Okay? We're nowhere near 10% accurate at those. Right? So we've got those to work out, and then once we've done all those, we then have to take mock observations. And Gus mentioned that a bit. I mean, you mentioned the BCC, the Blind Cosmology Challenge. So that's you give the observers some mock observables that you've made with all these things, and you get them to try and do some science with them. Okay? That's totally unexplored terrain as to how accurate it is, right? I mean, you've done some work in it, but basically it's hopeless. Right? They're miles away from getting anything to work. Right? Realistically. I mean, a factor of 3 would be good. Right? I'd believe them if they told me something was 10 to the 14 and something else was 10 to the 15, but I wouldn't believe them much more than that. Right? So, where are the problems? As I've shown you, 1% code stability above, bigger K than 1 is hard. Okay? You can do it, possibly, but it's hard. Getting to K equals 50, total dream. Okay? Even n-body only. And that's because also that's where the neutrinos kick in, that's where the baryons kick in. We have no idea how that works. Lots of open models there, right? And that's also where the modified gravity signal comes from. Okay? And then after that, we've got to populate this structure and recover the observables. And these are really wide open areas to work on. There's some computational problems. Okay? Data storage. Ilyan mentioned this as being a real bugbear of these large simulations. Lots of these computer centers only allow you to keep the data for a year, max. It's just not long enough. And you just physically can't get this size of data off the machine. So you're completely stuck. Okay? So that's difficult. And the other thing we need to think more about is engagement. So the reason the Millennium simulation worked really well is because lots of people used it. And that's because the data was made available in a format that many, many people could pick up. Okay, so it's no good simply running a simulation and dumping particle positions onto a disk, right? Because no one's ever going to use that. So you've got to do data reduction, and you've got to make that data reduction basically galaxy catalogs nowadays in a format observers can use. And then you've got to go out and sell it. Okay? It's no good doing the MXXL and just leaving it on disk. You'll get 0 papers that way. Right? Like the benchmark is the Millennium, like thousands of papers. Okay? And I thought I'd throw in this slide about why going to exascale. Why exascale? Well, fundamentally it's because we want to do some more science. Okay? If we're going to do science, then we need to get this underlying framework right. That means we've got to get the ICs, we've got to get post-processing, we've got to do all the individual steps at the accuracy required by the data, by the observational data we're trying to match. And that currently, they claim, is 1%. Okay? That's what we've got to aim for. And that means we've got to push past k equals 1, right? Which is hard. If we're going to do that, we've got to think about baryonic physics, the stuff that Richard was talking about. Okay? So we really, really have to work. We need lots and lots of CPU to do that because there's lots and lots of parameter space to look at, and then we need an enormous simulation with it in. Right? But why exascale? Here's another justification. Several people have claimed to be doing petascale, vaguely, right? So we're only a factor of 1,000 away from exascale, right? Now, a factor of 1,000 is nothing, because we have 3 spatial dimensions, so that's 10 cubed, okay? So that only means you need a factor of 10, but also, when we go up in resolution, we have to lower the Courant factors, we have smaller time steps, so actually we get another factor of n, just from the fact that we've got much smaller time steps. So the effort goes up at least as n to the 4th, right? But not only do we do that, we add extra physics. We have to think about feedback and all these things that happen on smaller scales. So I would claim actually that the scaling goes at least as n to the 4th, and it's probably closer to n to the 5th. Now, if you're scaling something at like n to the 5th, you only need a factor of 2 or 3 before you've got a factor of 1,000 in effort. So to answer the computing question as to why do we need exascale, actually we don't need to go up much in resolution. Right? A factor of 2 or 3 in resolution gets us a factor of 1,000 in effort. So if your exascale computing challenge is effort-based, then we can do that. But there's a caveat to that. We have to give up on these enormous n equals 48 billion trillion simulations, right? Because they're just killing the market. Because in order to do science, we don't go up that much in n. We might only go up in n by a factor of a few, right? Because of this large scaling with the extra physics, okay? And so we have to realize that these large exascale computing might involve poorly using the machine, poor load balance, very high memory usage. That comes with the territory. It's expensive to go to high end. Biggest issue, people, right? We desperately need people. Computing cycles we've got lots of. We desperately need people to do the physics, to implement these algorithms and test them, and to play around with them, right? And we really need to lobby the people who fund these science missions. What is the point of funding a 200 million euro, 250 million euro satellite mission and not funding any science? It's totally crazy. It's just a slush fund for funding satellite builders. It's nothing to do with science. And that's the problem. We should lobby them. If they want to fund the satellite mission, they need to fund the science. And that means they've got to put money into people, not just building the thing that goes ping. Okay? And if you're going to do that, you need to retain these people. If you're going to retain them, you need a career path. We don't have a career path for people who do this stuff. They come along, they do a PhD, they stay for a postdoc, and then they're completely stuffed. Okay? That's a serious problem. So here's my take-home message. You can read it for yourselves. Physics is expensive. We need to think beyond just building massive computer systems and running them close to peak. Thank you.